why don't you guys try to solve this one? dy dx equals 2x. Have fun. Right? This is the simplest differential equation I could have given you, right? I mean, are there steps at all? Well, I guess I could separate the variables. When I take the antiderivative of dy, I get y. When I take the antiderivative of 2x, that's x squared. And I need to remember to put a plus c. That's right. Okay. So here I have a one parameter family of solutions. Yes, integral curves. Good. Now, let me show you another problem that you might be assigned. Y prime equals 2x, comma, y of 0 equals negative 1. This is called, yes, this is an initial value problem, and you're right, this little piece of it is called an initial condition. That's right. This is an initial condition. That's right. That's right. Okay? And by the way, I may as well show you guys something that the book does, which I don't want it to confuse you because I tend to do things differently. The book would write this. dy dx equals, instead of writing equal to 2x, they might write this. Minus 2x equals 0. And then they like to set the equation equal to 0 and write this. Maybe they would write this. Negative 2x dx plus dy equals 0. And what they have done here is, again, separated the variables. This time, not onto separate sides of the equation, but on the same side of the equation. Are you with me? Yeah, minus 2x, because what we did was we subtracted 2x from both sides to get it. You see? Yeah. Okay. So the book puts everything on the left. And I'll show you why in just a second. Okay? And then what the book is going to do is integrate. And when you integrate negative 2x, I guess what we're going to get is negative x squared, right? Plus, what are we going to get here? When I integrate dy, I'm going to get y. When you integrate 0, you get 0, but remember that we also get a constant? We get a constant for each of these. We can subtract them all to the right-hand side, and so the book is next going to write this as its family of solutions. Okay? Which, notice if I add x squared to both sides, what do I get? Same thing I got above. You guys follow? Rick? I'm sorry, what are you asking?
How did they change it into negative 2x plus dy?
Okay. It's almost like you're multiplying everything by dx, the differential. See, this is what I would call the differential form of this equation. It's the same equation as what's above. It's just that we moved the dx up into the numerator. Well, it's gone here, but now it's next to the negative 2x. Is that okay?
Yeah, they multiply the other side by dx to 0.
That's right. And that's one of the reasons we want it set equal to 0. If it weren't set equal to 0, that wouldn't work. Okay, and now we still need to use our initial condition, the fact that y of 0 equals negative 1. So what's that mean? It means if I put a 0 in for the x, I have to put a negative 1 in for the y. So let me write the equation down. It would be negative 0 squared plus negative 1 equals c. So what does that tell me? C equals negative 1. And that tells me the particular solution I want. The particular solution I want would be, and maybe I should have done it up here. Maybe it's a little easier. If you put a 0 in for x, c is negative 1. And so the particular solution I want is y equals what? X squared minus 1. This would be the particular solution that I get for this initial condition. And so if you just see a differential equation, you're going to get a family of solutions. But if you see an initial value problem, we're looking to get a particular solution, one integral curve. Does this make sense? Cool. So we'll try this one. dy dx equals 2xy. And then we'll also think about this one. dy dx equals x plus y. So there's two separate equations to think about a little bit. I guess the question I should ask is, are these separable? So this one we would mark as separable, and we're happy. We think we can solve this, provided that we can do the integration. This one, not separable. So I'll tell you, wait till next week. Just to give you an example of something that, not every simple differential equation is separable. Okay. But this particular one, let's see, what can I do? Well, I would probably write dy over y equals 2x dx. Then what? Okay, what do I get? So the absolute value of y is e to the x squared plus c. And then, what would I do next? Okay, so we could say y equals k e to the x squared. And I'm a little disappointed in myself. So I need to make a note that that's not the best example. I wish I had done this. Much better. How does that change the problem? Well, not very much, right? So I would get negative x squared up here, right? Why does that make me happier? Because that's a famous curve, right? E to the negative x squared. If you pick the right constant, you actually get the bell curve. That's right. Pi over something with this standard deviation, da-da-da-da-da. So this is a very famous curve now, and so I say, wow, that's kind of cool, but that's the solution to a pretty simple differential equation. Okay, I'll know better for next time. Negative. All right, and then this one's not separable. Rick.
I'm getting k times e to the x squared.
I changed the problem. You missed that? I said I wish I had put the negative. So then people allowed me to do that. Okay. So now what? Well, we better start doing ones that are slightly more complicated, because you know they're not all going to be simple in the book. Let's try, how about this one? The square root of 1 minus 4x squared times y prime equals x. Don't worry, it's not as bad as it looks. What would you do? Yeah, so I want to say something about this, which is that remember that my first goal is to see if I can separate the variables. Which variables? X and y, right? So we want to write this as dy dx, right? And so where are the x's going to end up then? On the right-hand side, okay? X over square root of 1 minus 4x squared. Time out! Time out! I just divided by a function. I better be careful, right? But I want to show you guys, I am going to do this all the time. I'm going to divide by functions all the time in this class. I just have to remember that I did it because, like Robin said, we better make sure that this function isn't 0. If that function is 0, what happens sometimes is there'll be a solution that's a solution to the differential equation that I kind of miss if I do that. Okay? So I'm going to go ahead and look for it in a little bit here. We'll see if it comes up. Okay. So I would write what? dy is equal to x over the square root of 1 minus 4x squared dx. And so now it comes down to just integrating both sides, right? And so y is equal to the integral of x over the square root of 1 minus 4x squared dx. Right? That is the answer. Are you with me? That's not the answer the book's going to have, because what's the book going to do? They're going to integrate it. Okay? And we should integrate it, and I will in a moment. But I want to point out, remember, can you always integrate? No, sometimes. For example, here's a classic example of a function I can't integrate. E to the negative x squared. Did you guys know that? Not even with parts. Some people would argue that's the most important function in mathematics, the bell curve, the normal distribution. And if you take a statistics course, even to this day in the back of the book, they have a whole list of values of the area under the curve, a whole table, because those represent probabilities. How'd they find all those if you can't integrate it? Numerical methods, things that you may have learned about called the trapezoidal rule, or Simpson's rule, or other things. Who was your Calc 1 teacher? No, anyway. But all these ways of finding the area can be useful. And so I want to point out something, guys. This answer here is just fine for lots of scientists. They'll write it down, and they'll say, hey, let me type that into my computer. It'll spit out a numerical answer. Close enough. You guys follow? Now for us, what are we going to do? Sure. How? Use substitution. Yeah, Rick?
If you're going into a field like I am meteorology,
Yeah.
computer modeling,
Yes.
would you put, would there be functions like that in there that they
I think so. I think your computer should be able to handle this, honestly. Especially if you know the limits of integration, which you may. Okay. Now, anyways, let's go ahead and do the integration. So what are we going to let u equal? Yeah, that's the trick, is let it equal the whole 1 minus 4x squared. And now du is going to equal what? Negative 8x dx. I have a question. Is this the form you guys use when you do u substitution?
Yeah.
You know what that is? That's a differential equation. you're writing it in differential form. I don't know if any of you guys had Armstrong at some point. Armstrong likes to do this. He'll go du dx is negative 8x, which is a really nice thing to do when you're first learning. And then we separate the variables. So you've done this before. Okay, but once I write these things down, I say, oh, wait a minute. I don't have du. I almost do. I have x dx, but what do I wish I had? Negative 8x dx, right? So what do I do? Right, so we get that y is equal to, well, negative 1/8 of the integral of u to what power du? Well, the du is going to be there now because I multiplied by negative 1/8. So it's u to what power? Negative 1/2, okay. So now I'm getting there. And this is negative 1/8, let's see, times, well, I'm going to make it u to the positive 1/2, right? So that means I need to multiply by what? 2. Okay. Plus c. Don't forget the plus c. That's how we're going to get a family of solutions, right? And so I get, I guess, let's see, as a final answer, y equals, this would become negative 1/4, and now I'll put the u back in. The u is 1 minus 4x squared. Since that's to the 1/2 power, I'll put it as a square root. Square root of 1 minus 4x squared plus c. So any questions on this? Yeah. Why can't x be 0? So let's...
Not x, the 1 minus 4x squared is 0.
Right. If we had... So let's see. If we had the square root of 1 minus 4x squared equal to 0, that would be a problem. Right? That's what you're saying. And so let's go through and see what that would mean. That would be the same as 1 minus 4x squared equaling 0. So 4x squared equaling 1, x squared equaling 1/4. So x equaling what? Plus or minus 1/2 could be a problem, right? What is the domain of this function? You know, when I write that these are my solutions, maybe I should think about the domain. Isn't it true that we need 1 minus 4x squared to be what? It has to be greater than or equal to 0 in general, right? So we need negative 4x squared to be greater than or equal to negative 1. We need x squared to be less than or equal to 1/4. And so for this equation to make sense, we really need x, well, the absolute value of x to be less than or equal to 1/2, right? X to be between negative 1/2 and positive 1/2. My domain is from negative 1/2 to positive 1/2. But now what we're saying is, hey, maybe I should really restrict the domain to just negative 1/2, positive 1/2 for this to make sense, the open interval, right? That's what we're saying. Right?
In these last couple, several ones, how come we're using the custody and that kind of period of K like we did in the handout? That the E and a lot of people.
That's a good question. Does anyone have an answer there? Why is it that we have a C here rather than turning it into a K? See, if you look at the ones above, when I turned it into a K, notice when we integrated both sides, we had a natural log, right? Well, then what's the next step? E to the. You
Yeah.
undo it. And when you do an e to the, that gives you the opportunity to get y by itself, but then e to the c is k. But in this problem, I wasn't integrating dy over y like I did in that one. In this one, I was just integrating dy, so I already had y by itself. Okay, it's a different problem. Vince? Ooh, maybe. When I wrote down k, I didn't mean to represent anything in particular, okay? As a matter of fact, I think the book sometimes writes down capital A here, and I'm okay with that too. What I'm doing with this constant is I'm saying that this is plus or minus e to the c is what it actually is. Because remember, when we have e to the negative x squared plus c, that's the same as e to the negative x squared times e to the c. And that e to the c I can bring out front with a plus or minus, and then I don't need an absolute value. That's just a standard trick that we've done a few times now.
When we solve these, you want us to always find the domain right there.
I just want to give you an example like this. Y times the natural log of x minus x times y prime equals 0. Because this is the kind of thing you might see on the homework. Okay? It's a little more challenging. I'll tell you it is separable. That's nice to know, actually. Which is kind of what you know on the homework, right? Section 6 is on separable equations. You're assuming they would give you something that is separable. Yeah, Rick?
How do you tell if it's separable from one point? Does it have to be a product or something to be
Is this a product of something?
It's y times we have a outline of a variable and then x times y prime product. Assuming it is this.
I'll be honest with you. At first glance, I don't know. I have to think for a while. I have to do some work. Let me show you what I would do first. If I'm going to be thinking about separating variables, which is I'm telling you is a great thing to think about when you get a differential equation, why don't we do that first? Okay? Equals 0. That's okay? What do you think I'm going to do next? I'm going to, quote, multiply by dx. Now again, what is a differential? Let's not worry about that now. Let's be just follow the motions. Formal mathematics, I could write y natural log of x dx minus x dy equals 0. Are you guys with Dave there? Let's divide by y, divide by x, and then I think everything is nice and separated now, right? So we get natural log of x dx, it's going to be divided by x, minus dy divided by y equals 0. And again, if you wanted to bring stuff over to the other side, I'm okay with that. I thought I'd show you one like the book would do. Okay? Is this okay? Now what am I going to do? I'm going to be integrating. Okay? I'll make a deal with you guys. I'll do the y's, you do the x's. You're welcome. And I'll even do this. The integral is 0. I'm going to put a c here. And then when I integrate dy over y, I think I get, I've seen this one before, natural log of y. Okay, it's that first one, huh? You see it? You may be able to do it by parts, that's true. If you know what to substitute. What do you let u equal? The trick is, you let u equal something you know the derivative of. That you have. If you let u equal the natural log of x, I think Christina said that, I think that's the easiest way. That's what I would have done. Because then what's du equal? 1 over x dx, which I basically have right here, right? Right? Because dx over x is the same as 1 over x dx. So let's see. What I end up getting is the integral of u du. Okay? So let's see what we get. Well, we get 1/2 u squared minus ln of y equals c. And so let me fill things back in. I guess I get 1/2 the natural log of x quantity squared minus the natural log of the absolute value of y equals c. Guys okay? And can I do any better than that? I mean, not really. Not really. Can I simplify at all? How would you solve for y? Okay. I'll be honest with you. I might actually stop here and check the book at this point and see if that were the answer. Those are from the book. But let's go ahead and give it a shot like Evan suggested. So, even though it's almost breakdown. ln y equals 1/2 ln x squared plus, well, minus c, if you want, plus c. You know, you could make it a plus c. And so, you don't like the minus c turning into a plus c? I could call it plus c2. Rick, you look.
Why did you choose dx over x instead of leaving it 1 over x dx? I know how you got there.
Those are the same. I'm just trying to say they're the same, and I noticed I had a dx over x,
Okay.
which is 1 over x dx. And then, so basically that pink part became my du. And then I noticed the only other thing I had was u. Okay? I think because we're at break time, guys, and because I don't think this is going anywhere, I'm going to stop, and I'm going to say that we have a solution here. What kind of solution? Do you know that? Remember the word? I'm going to say we have an, how about implicit solution? And you're right, one parameter family. But do you understand what I mean by the word implicit? I don't have y equals and I'm telling you what it is, but I'm telling you that this is the relationship that kind of explains what the curves look like. And if I understood more about logs, maybe I'd know what the curves really look like. I don't. Okay?
We did get a solution.
That's right.